In computer vision, many explainable AI methods are gradient-based. In understanding how these work, the best place to start is by looking at the raw gradients of a network. These are called vanilla gradients. And really, in this video, we are going to focus on the limitations of this method and how other gradient-based methods can start to address them. These limitations include noisy gradients, irrelevant information, saturated gradients, vanishing gradients, and a lack of contextual awareness. And if you want a more practical take, then check out my video on guided backpropagation. It compares the output of that method to saliency maps generated using vanilla gradients. Before we get started, I'd just like to mention that this lesson is part of a wider Explainable AI for computer vision course. It's completely free and you can find a link to it in the description. You'll find the article version for this lesson as well as many coding resources. And there is a paid version of the course which I'll talk about at the end of this video. Simply put, vanilla gradients are the gradient of the output with respect to the input image. All we need to obtain these is guided backpropagation. Typically, backpropagation is used to calculate gradients that are then used to update the parameters of a network. This is also usually done with a batch of images. Vanilla gradients use backpropagation in a different way. We take one input image and find the gradients of the loss with respect to the pixels in the image. This is also called a derivative or rate of change. Intuitively, pixels with large gradient, both negative and positive numbers, have had a large impact on the loss. In other words, they are more important to the prediction for a given image. By visualizing all gradients, we can create a saliency map showing important regions in the image. For classification problems, we are usually only interested in the predicted class. This is the one that had the highest logit. So when calculating vanilla gradients, we will instead take gradients of the output logit for this class with respect to the input image. This will tell us how important the pixels are to the predicted class and not all logits in general. We've touched on it already, but it's important to clarify the interpretation of gradients. Using methods from the permutation-based section, we could make claims like a specific region of pixels has increased the prediction. We need to be careful when making these same claims using gradients. That is, when interpreting gradients, we should focus on their magnitude and not their sign. This may be confusing when we consider how gradients are normally used. When doing backwards propagation, a positive gradient indicates that we should decrease a parameter to decrease the loss. When looking at the gradients of a logit, this interpretation switches. A positive gradient indicates that we should increase the value of the parameter to increase the value of the logit. In other words, we can say a positive movement in the parameter supports the prediction. But when looking at the gradients of an input pixel, it is no longer clear which direction should be associated with supporting or opposing a prediction. For example, take a model that classifies images as either a dog or a cat. Suppose the pixels on a dog's nose have a positive gradient. This suggests that increasing the pixel values, making them slightly lighter in color, would increase the dog logit. However, if the gradients were negative, we could similarly increase the logit by decreasing the pixel values, making them slightly darker in color. But why should one color change be associated with supporting the prediction and not the other? In short, the direction in which we change a pixel's value has no causal interpretation. This means that we could say that a movement in the pixel supports or opposes a prediction, but we cannot say that the pixel supports or opposes the prediction. Ultimately, we cannot make conclusions around how a pixel has influenced the prediction, only that it is important to the prediction. This interpretation of vanilla gradients is one of its weaknesses. It means that we should really focus on the magnitude of the gradient, but as we'll see, even this has its problems. The biggest problem is that gradients can be extremely sensitive to small changes in the input. This means that small movements in a pixel value can lead to large changes in the magnitude or even flip the sign of a gradient. This can lead to saliency maps that are hard to interpret, as they appear speckled or random in regions that should probably be smooth or semantically meaningful. A method called smooth grad has been shown to help. I think the paper's subtitle sums it up: adding noise to remove noise. It works by augmenting images by artificially adding noise, and then we take an average gradient across all the augmentations. This helps reveal more consistent patterns, and keep in mind this method can be used on top of any gradient-based method and not just vanilla gradients. A related problem is that we can often see rapid swings in the signs of the gradients. For this image, positive gradients are white and negative gradients are black. And if the gradient sign from all channels is not the same, the pixel is given a gray color. You can see how the sign changes even in semantically similar regions. This has to do with both the sensitivity of the gradients and the non-linearity of neural networks. Ultimately, this emphasizes the point that we should be taking the absolute of the gradients. This is especially true when you want to aggregate gradients over different regions of the image. The previous two problems could be summarized as one, and that is noisy gradients. Another factor that contributes to noisy saliency maps is that often gradients can contain information that is not specific to the target logit. Often, we only want to understand regions or features that support a prediction. However, gradients can be large in regions that suppress the predicted logit. These can come from pixels in the background or those from features associated with other classes. Guided backpropagation can clean up saliency maps using a process called ReLU masking. This alters the ReLU activation functions of a network, so it suppresses negative gradients during backpropagation. The result is a visually sharper saliency map that highlights the features used by a model. However, this method is not class discriminative, meaning it may still highlight features useful for multiple classes, not just the target one. GradCam is a more reliable class discriminative method. It aggregates the activated feature maps in the last convolutional layer of a network. By focusing on deeper layers that have more semantically meaningful features, GradCam can identify regions that support a specific prediction. And we discussed this complementary relationship between guided backpropagation and GradCam in the lesson on guided GradCam. In some cases, the gradients of important pixels can still be small or even zero. Take the ReLU activation function. During backpropagation, if the input to the function is a negative value, then the gradients will be zero, regardless of how large the negative input is. This is true even for very large negative values, which is an indication that the input is important to the prediction. This can lead to regions in the input where the gradients become flat, giving us a saliency map that suggests they are not important. Integrated gradients overcomes this problem using a baseline image. This is an uninformative, usually all black image. This method takes an average of gradients computed along a straight line path from the baseline input to the actual input. This avoids the saturation problem as we do not observe gradients at a single point. Instead, we observe how they change over the path. Vanishing gradients is a similar problem. In large networks, during training, the gradients of earlier layers can become small or even zero. This is because they are obtained by iteratively multiplying gradients of deeper layers, which are small values themselves. By the time we get to the image, the gradients may indicate that a pixel isn't important, even if it's used in deeper layers. Thankfully, this problem has largely been solved by changes to model architecture. Using mechanisms like residual connections and normalization, we can avoid vanishing gradients in training and subsequently in our interpretations. Although it is worth mentioning that GradCam wouldn't be impacted by this problem. This is because it uses the gradients from deeper layers in the network. Our final problem is that vanilla gradients reflect local sensitivity. That is how a small change in an input pixel would impact the output. This does not capture how specific features or regions in an image contribute to a prediction. Due to interactions, the impact of changing a collection of pixels is different to the aggregated impact of changing them all individually. Consider the image of a school bus. The model may be able to classify this correctly, but it is unlikely to rely on an individual pixel to do this. Likely, a yellow pixel in the context of many other yellow pixels has increased the school bus logit. Both the presence of wheels and the yellow body could increase the score. Even the presence of the road under the bus might have contributed. It is all these aspects working together that give us our final prediction. Ultimately, due to the non-linear nature of neural networks, we might miss important details when focusing on individual pixels. Integrated gradients mitigates this by changing all pixels simultaneously. GradCam also mitigates it by focusing on the gradients of deeper layers. As we progress through the layers of a CNN, we go from simple features like edges and textures to more complex ones like object parts, then entire objects. So the elements of these deeper layers contain more detailed semantic information. In other words, they will likely contain information about the interaction between different regions or objects in an image. As mentioned, in the course we go on to apply vanilla gradients using Python. This helps demonstrate some of these limitations that we discussed. With vanilla gradients, we can still see some important regions. In this case, it looks like the table and glass are contributing to the prediction. However, there is a lot of noise in the output. Potentially, all the limitations that we discuss are contributing to this. However, the problems around noisy gradients are the most likely culprits. As I mentioned, this lesson is part of a wider explainable AI course for computer vision. There, we go into details on methods like occlusion, SHAP, GradCam, integrated gradients, and guided backpropagation. That course is completely free, but there's also a paid version where you'll get access to a course certificate, quizzes, all of the videos ad-free, as well as an ebook which allows you to access the course content offline.